last couple of classes, we've looked at methods, techniques, algorithms for digital filtering. We looked at digital filtering both in the time domain, we spent most of our time there, and also in the frequency domain. We spent a little bit of time there. All of these methods are designed for denoising, or picking the signal out of the noise. And we talked about the example of picking the gravitational wave signal out of the noise of seismic activity and traffic and other things. In the next couple of classes, so we got today's class, and then we got next Tuesday's class, and then we're done. We're going to talk about interpolating data, interpolating discrete data with some sort of interpolation function through that discrete data. Here, I'll just show an example in today's class of a practical application of interpolated data that's close to me, which is in the measurement of the muon's anomalous magnetic moment. We have to interpolate data. We have to interpolate data on magnetic fields and particle distributions to convolute those two things together. So I'll mention that. In today's class, we're going to spend our time on interpolating the data or a set of data, an example set of data, with a single polynomial. So we're going to set ourselves the task of putting the best polynomial possible through a set of data points. And I'm going to describe a couple of ways that we can do that. A linear algebra way that you can put a polynomial through a set of data points, and then a Lagrange polynomial method for putting a polynomial through a set of data points. I'm talking about interpolation. Partly we use interpolation in a lot of physics, but interpolation is really the cornerstone or a foundation of machine learning. So you can think of machine learning as basically interpolating data, say interpolating training data, and then generalizing the results of that interpolation to trial data or new data. So the work that we do on interpolation in today's class and in next Tuesday's class is a sort of foundation of what goes on in machine learning. Because interpolation is a fundamental in machine learning. Okay. Before computers, before the modern era, the ancients were interpolating. So a famous example of interpolating is ancient astronomers interpolating the position of objects, astronomical objects, and they would use those interpolations to determine, for example, the date of solar eclipses, lunar eclipses, other astronomical events. So interpolation's been going on forever. Present day, interpolation has become a big business. I just got one example and then a general comment of interpolating here. So if you want to resize an image, if you've got a digital image, we want to resize that image. We want to make that a bigger digital image. We can resize that image by interpolating between the pixels to make an image that has more pixels. So that's an example, a specific example of interpolation in 2 dimensions. Present day engineering, science, math, medicine relies on machine interpolation, machine learning for so many things. So it's a very important topic. I wanted to just show you the interpolation that I'm familiar with from the muon G-2 experiment. The muon G-2 experiment is this project to measure the anomalous magnetic moment of muons. The muons have a magnetism, a magnetic moment. A little piece of that magnetism, that magnetic moment, comes about from the fact that the vacuum is filled with virtual particles, electrons, positrons, photons, up quarks, down quarks, so on and so forth. And measuring that anomalous piece of the muon's magnetic moment is a test of our understanding of what the fundamental forces and what the fundamental particles are. So we measure the magnetic moment. Measure the magnetic moment by storing muons in a magnetic field. And we measure the precession of the muon spins in that magnetic field. But to interpret the precession of the muon spins in that magnetic field, we need to know the magnetic field where the muons are. We have to convolute the distribution of muons in the storage ring with the measured magnetic field in the storage ring. So there's two interpolations that we do that are foundations, cornerstones in the experiment. Make some measurements of the magnetic field in the muon storage ring, and we have to interpolate that to find its distribution smoothly throughout the storage ring. We measure the positions of individual muons in the storage ring. We have to interpolate that result to convolute with the magnetic field distribution. So at the heart of muon G-2 experiment and the determination of the muon's anomalous magnetic moment are two interpolations. One, an interpolation of individual measurements, discrete measurements of magnetic fields to get a magnetic field distribution, individual measurements of muon positions in the storage ring to get a muon storage ring distribution, smooth storage ring distribution. This is inside the storage ring. It's like this circular tunnel that the muons are heading around. Inside that storage ring is the magnetic field that the muons live in. Inside that storage ring, the muons are distributed in some region. And just to show you, this is the distribution of muons in the storage ring, measured from data on lots and lots and lots of individual muons. And we interpolate this distribution to get a smooth function describing the muons in the storage ring. So that's a two-dimensional interpolation. And then this part here is the magnetic field in the storage ring, contour map of the magnetic field in the storage ring. This also is measured at fixed points in the storage ring, indicated by the crosses here. And then we interpolate that to get a smooth two-dimensional distribution of the magnetic field in the storage ring. And it's only through these two interpolations, the muon distribution, magnetic field distribution, and then the convolution of those two distributions. We talked about convolution last class. We're able to extract the anomalous piece of the magnetic moment of the muon and test the standard model. So we're doing interpolation. It's a big part of the project. Okay. So stepping back, for today's class, we're going to take some simple data. Some simple data that is just a collection of X, Y data points, independent variable, dependent variable data points in one dimension. And we're going to interpolate these data by putting a single polynomial through these data points in today's class. And in the next class, Tuesday's class, we'll put a piecewise collection of polynomials through the data points. So there's two ways that you can interpolate. So on this plot here, I'm just imagining that I've collected from some detector or some sensor or some instrument, some collection of data points that are X subscript i's, the independent variable, and Y subscript I is the dependent variable. And I just plotted them over here on the right-hand side of this figure. In this case here, just a few data points. In interpreting this data, understanding on this data, or modeling this data, using the physical laws for this data, we want to put a smooth line through this data. So what we're interested in is, can we represent this data by a smooth function that passes through these data points? Can we learn from these data points what is the smooth function that passes through these data points? That would allow us to predict values in between this set of data points. We would in that way be learning from the data points. So we want a smooth function, I call it f of x in blue here, that passes through this set of data points. The case that I'm going to talk about in today's class, and actually the case I'll talk about in next Tuesday's class, is a special case of pulling a polynomial or polynomials through data points. I'm going to focus on the case when the data points are equally spaced in the independent variable. Of course, you could have data where they're not equally spaced in the independent variable. It just makes our work a little bit more complicated, but the same idea, the same concepts apply. We're going to restrict ourselves, like we restricted ourselves to a one-dimensional set of independent variables. We're going to restrict ourselves to equally spaced independent variables. So I'm going to do that. We're going to use a matrix algebra method to find this smooth function f of x that passes through this set of red data points. And we're going to use a Lagrange method, Lagrange polynomials, to find the smooth function f of x through these data points. So we're going to walk through on the next couple of slides just two methods of finding what this smooth function is that I've drawn as going through this set of data points, going exactly through this set of data points. And then we'll just see on two slides how to do it. And then we're going to implement it on a computer. Okay, so we're going to consider putting a nth-order polynomial through our set of data points, n plus 1 data points. And if you've got n plus 1 data points, then you can, a polynomial of order n can pass exactly through those data points. So we want to find out the coefficients of that polynomial that passes through those data points. And so I've set up this problem here. I want to find this polynomial upstairs here, an ordered polynomial that passes through n plus 1 data points. n plus 1 pairs of xi's and yi's. To pass through those data points, each of those data points represents a equation for the coefficients of the polynomial and the values of the independent dependent variables. And so we have a collection of n plus 1 equations for the n plus 1 data points that relate the data point values and the coefficients of the polynomial. And I can write that compactly. We've done this before as a vector matrix equation using matrix algebra. And so that's what I've written down here. That matrix equation, each line of that matrix equation is corresponds to carry out this matrix equation. Each line of the matrix equation corresponds to one pair of data points and one relationship between the data points and the coefficients of the polynomial going through the data point. And the collection of these equations would allow us to solve for the values of the coefficients of the polynomial that goes through all of the data points. So if we look here, the matrix is called the van der Waals matrix. We met this before. Its columns are increasing powers of the dependent variable. So here we've got a column of the 0th power, the 1st power, so on and so forth. We've got a matrix over here, a vector over here, which is the dependent variable, and then we've got the unknown coefficients here. So if we look at this from what we know, what we don't know, we know the matrix, we know the vector dependent variable. Because we know the independent and dependent variables, we want to solve for the coefficients here. So this is a matrix algebra problem of solving this equation, knowing the matrix, knowing the vector on the right-hand side here, wanting to solve for the vector here, that's multiplying the matrix. And we can solve this by just multiplying that equation through by the inverse of the van der Waals matrix, the inverse of M. That'll give us a unit matrix over here on the right-hand side, and it'll allow us to solve A as the product of the inverse of the van der Waals matrix times the vector one. And so that will be one approach to finding the coefficient of the polynomial that passes smoothly through all our data points, our interpolating polynomial. And we'll go ahead and use the linear algebra in NumPy to apply this approach to find this polynomial. We'll compare it with a second way of finding the n-order polynomial that passes through n plus 1 data point, which is to use a kind of what's called a Lagrange method, and which uses a Lagrange basis polynomial to determine this unique polynomial that will pass through the data points. So the idea here is that the interpolating polynomial, I'm still calling the interpolating polynomial p of x, that interpolating polynomial can be written as a summation of Lagrange basis polynomials, a weighted sum of Lagrange basis polynomials. And that's this expression here. So based on your number of data points, the interpolating polynomial can be written as a corresponding sum of these Lagrange basis polynomials, whatever they are. I haven't said what they are yet. And the weighting factors for all of those Lagrange basis polynomials is just the values of the individual values of the dependent variables, the yi. The Lagrange basis polynomials, I call them this cursive L here. They have this index I that runs from 0 to the number of data points that we have, to n plus 1, the number of data points that we have. They're given by this little expression here. In that expression here are the xi's and the xm's are the individual values of x at the data points, at the location of the data points. And then the x's without the subscripts are the variable x. So these are polynomials in x because of this x here without the subscript. That's the variable. The others are the discrete values that you measured, that were part of your measured data. So this little expression here, so this is a product of these terms over this this series here, rather than a summation. This expression here has the important properties for a basis polynomials is that, for example, you took L0, it would be equal to 1 at the value of x0, and it will be equal to 0 for all the other values of your independent variables, so x1, x2, up to xn. So L0 this little arrangement here, this arrangement causes L0 to be equal to unity at x0 and L0 to be equal to 0 at all the other x values, x1, x2, and so forth and so on. Likewise, L1, this combination here arranges that L1 is unity at x1, but it's equal to 0 at all the other values. So x0, x2, x3, and so on and so forth. And so on for L2 and L3. Right? These basis functions are non-zero, equal to 1 or one of the data points, and 0 at all the other data points. Now, that allows you to construct, if you add those, if you combine those polynomials, you make a summation of those polynomials, and you weight them by the values of y at the locations of each x. You can imagine that that curve will go smoothly through all the data points. So if you weight the value of L0 by y0, multiplied by y0, it will go right through the x0, y0 data point. Do the same thing for all the other terms. It's a way of constructing a polynomial with these basis vectors, basis functions that goes through all the data points. And so this is arranged with this definition of the polynomial to go through all the basis points. And so this is a second way that you can come up with, rather than the linear algebra method, come up with the polynomials that are going to go through the interpolating polynomial by calculating these polynomials here, by weighting them with your values of y. That will be the polynomial that goes through the data points. Yeah.
Oh, I was wondering, so could you maybe go back to one slide to the matrix?
Yeah.
I'm just interested because, so those A coefficients, or like the vector that's the diagonal axis of the Vandermonde.
Mm-hmm.
What's this significance of the diagonal elements of the Vandermonde matrix in here?
Of the diagonal elements?
Well, just or the eigenvalues, I guess. Like the solution you get. Well, I guess y is not.
I would say the Vandermonde matrix comes about. I don't know how to answer the question of eigenvalues and eigenvalues, but the Vandermonde matrix comes about, in my experience, as a non-mathematician, came about when we did least squares fitting. And when we did least squares fitting, we fit to, a linear function or a polynomial function. And the Vandermonde matrix came about when you wanted to represent those polynomials that you were going to use for your fit. And it's coming about here because we want to interpolate with a polynomial rather than a fit. And so we wanted to represent the linear equations corresponding to the interpolation. So it just came about in both the fitting case and the polynomial interpolation case because we were using a polynomial. We were using something that had a series of higher and higher powers of the independent variable, and we would have multiple copies of it for each of our data points. And I think it's nothing more than that. When you want to write that compactly in terms of matrices and vectors, you naturally get the Vandermonde matrix.
Okay.
Yeah. Yeah.
So these two pages, like the matrix and the Lagrange one, they don't require equal space, right, of x.
These, I think that's probably, I think that's right. Yeah. These do not require equal spacing. I know I said I was going to just treat equal spacing. And But I think you're absolutely right. These don't, it doesn't, yeah, I can't see why it would matter for these two, that it was equally spaced, actually. I think I'm anticipating something later on when I said the equal space. But yeah, you're absolutely right. So that was a very good point. Okay, so anyway, I introduced these two methods, the linear algebra method and the Lagrange basis method for finding the polynomial. And I'm going to go to the code and use these two methods to find the polynomial. Now, firstly, we're going to be finding the same polynomial in both cases. These are just two different ways of finding this polynomial. And in the past, I think the history behind it was the Lagrange basis vectors may have been a less labor-intensive approach if you didn't have computers to find the polynomials when you had a largest number of data sets, the data points. And nowadays, the matrix approach is, a simple approach if you have computers and computers that can handle vectors and code like Python that can handle vectors and matrices. So they were just in the history of developing the polynomial that went through the data points. These are just two steps in that history. Okay, I'm going to go to the code. And I'm going to start with a really trivial example so we can sort of follow the calculations in detail. I'm going to imagine that we've just got two data points and we want to find the interpolating polynomial for those two data points. And we're going to find that interpolating polynomial by the linear algebra approach that I laid out with the van der Waals matrix, and through the Lagrange approach using the Lagrange basis polynomial. Now, this is a problem if I've just got two data points and I want to find the lowest order polynomial that goes through that pair of data points. This is a simple problem that we could do in our head, basically. Look, if we got two data points, then a polynomial, so n plus 1, the same number of data points, equals 2, then a polynomial of order n, which is 1, will go through these data points. So a straight line will go through these data points, which is what we know intuitively, right? If I got two data points. So here we're going to be finding the straight line. That's the lowest order polynomial that will go through this pair of data points. If I'd had three data points, so a total of three data points, so n plus 1 equals 3, then a quadratic would go through the data points. That would be the lowest order polynomial that could go through all three of the data points. If I had four data points, then, so n plus 1 equals 4, then a polynomial of order n equals 3, a cubic, would go through those four data points. So that's always the rule, the recipe for the lowest order polynomial that can unequivocally go through your data points, no matter what your data points are. Anyway, so we're going to pick, I'm going to work with two data points here, and I'm just going to pick arbitrarily for this example the values of the dependent and independent variables for these two data points. So I picked a point that is 2, 1.5, my 0 data point, x and y values, and 5 and 4 for my second data point, the x and y values. And so I'm just defining on this, in this one cell here, a little array, NumPy array, to contain my dependent contain my independent variable and a little numpy array yi to contain my dependent variable. And just to verify the stupidity, here are two data points. There's one downstairs on the left, there's one upstairs on the right. We want to find the polynomial that passes through these. Obviously, with the two data points, we could find the slope of the line that goes through them, the intercept of the line. We've determined the polynomial by a very basic method. Okay. So in this cell, I'm going to solve the problem using the matrix algebra approach. And in the matrix algebra approach, we made that van der Waals matrix, which has columns that correspond to the various powers of x in your interpolating polynomial. Our interpolating polynomial has just a constant term and a linear term. So we're just going to have two columns in our van der Waals matrix. One that is just filled with ones. So that corresponds to x to the power 0. And then one is just filled with the array of x values. So that's the first power of x. And so that's my van der Waals matrix that I'm creating. I think we used this column stacking before when I previously made in the fitting case. We again had to deal with the van der Waals, built the van der Waals. We now go to my matrix, and I've already got my xi's and my yi's, my dependent and independent variable vectors, and all I want to do is solve that linear algebra problem from the slide that NA equals yi, and that problem is the solution to that problem. We can use this function here, solve. It solves that linear algebra problem for the coefficient A. So I'm just going to call that function. Input are our knowns, which is the matrix, which contains the independent variable, the vector yi, which is the dependent variable. So the arguments basically are the data points, and what it returns is the coefficients of the polynomial that's going to pass through the data point. So that's the solution to the problem, and then I'm just going to write out the values of the coefficients, and we'll take a look at the matrix. I'm going to plot the results. So I introduced here just a proxy for a dependent continuous variable x. I define a function as a proxy for the solution using that x, and the coefficients of the A0 and A1 that I got from my matrix algebra solution here. And so this is my interpolating polynomial that I've called y here in terms of my independent variable proxy, that's the x. And I'm just going to plot that. So finding that polynomial is straightforward using this method. But the advantage of this method is that you could imagine that this is very easy to extend to more data points in higher order polynomials. So if I had 3 data points and I want the polynomial that passes through the data points, then I just have I'd have a third column in my van der Waals matrix, one with xi's squared. I'd have, my xi's and yi's would have 3 data points, not 2 data points. But the solution would be to call the same function here, but now it's been called with a 3x3 matrix and a 3-element vector, and it would return an array of coefficients or a vector of coefficients that have 3 elements. And if I had 4 data points, right, I would just construct in the same way the van der Waals matrix, but I would have 4 columns with a to the 0, a to the 1, x to the 0, x to the 1, x to the 2, x cubed columns to it. My vectors for the dependent and independent variables would have 4 elements in them, and I would call the same function again, but now it would be returning an array of coefficients that have 4 elements. So this is a rather generalizable yeah.
So the x idea already have different powers of x. Or
Yeah, so here I got 2 data points. So that means what is the lowest order polynomial that goes through data point?
yeah,
Is that number of data points minus 1. So it's a linear. It's a linear function. So I just need these first 2 terms to make the van der Waals matrix. And if it was 3 data points, then what's the lowest order polynomial that goes through the 3 data points? It would be a quadratic. And so I just need a van der Waals matrix that would have 3 terms in it up to the x squared. Okay. Let me run it. Just take a quick look here. I did print out the van der Waals matrix that we constructed. The first column, so just to look at it, not much to look at here. So that first column is the 1s, and then the second column is the first power of the x, just the xi's, and the xi's were 2 and 5. And so we're just seeing what that looks like, but we just constructed it out of our xi. Second thing I printed was the values of the coefficient of the terms in the polynomial. So I printed those out, and it was the solve function in num_p or psi_p, depending on what package you're using. So it returned these values. So these are the coefficients of the interpolating polynomial. With those coefficients, I constructed that interpolating polynomial, and I added it to the plot of the 2 data points, and we see that, we would expect, right? It's going to pass through exactly through those 2 data points. And so this is the unique polynomial, that lowest order polynomial that passes through the pair of data points. Okay. And we solved it with this one line called the num_p or a psi_p function. One line called after we've constructed our vectors and our matrix. Second approach was the Lagrange basic polynomial approach. So in this approach, rather than constructing the van der Waals matrix, we would be constructing the first step would be construct the basis polynomials. So these are the polynomials that I call the cursive L's, is the symbol for the Lagrange basis polynomials. They have an index L on them, I on them that run over the number of data points. So if you had n+1 data points, that index was running from 0 to n. We've got 2 data points in our particular case, so we're going to have 2 Lagrange basis polynomials. They're going to have the indices L0 and L1. So I've got to construct L0 and L L1. And I just did that here. literally by using that equation that I quoted for the Lagrange basis polynomials on a slide describing this approach for finding the interpolating polynomial. So for L, if you use that equation, this is the equation for L0. And the second line is the equation for L1. Remember, in those equations, for the basis polynomials, there was an x without a subscript, which is the variable. So that's the x here. So think of this as this is our proxy for a continuous variable. That's in the numerator. But the other x's are just the x values for the corresponding to the different data points. So the important thing about the polynomials is and the usefulness of the polynomials is that Lagrange, again, is arranged that, for example, if you take L0, at the value of x0, it's equal to 1, and that the value of x1 is going to be equal to 0. So look, if I plug in for x1, well, this is x1. The numerator makes it 0. If I plug in for x, the value of x0, plug in the value of x0, then what's in the numerator is the same as what's in the denominator. It is 1. So this does arrange that at the 0th data point, it is unity, and at the second data point, it is 0. And the reverse is true for the second Lagrange basis factor here, function that we're going to use. This one is unity at the second data point, and it's 0 at the first data point. It's going to be 0 at the first data point because the numerator becomes 0 at the first data point. So those are two basis vectors that have that key property, and the interpolating polynomial is the first basis vector times the value of y at that first data point. So then that's going to go through that first data point, plus the second basis vector, which is unity at the second data point. If I multiply by the y value second data point, it's going to go through the second data. And so by construction with these basis vectors, that interpolating polynomial, if we weight it in this way with its two y values for the two data points, is going to go through the data point. This will be, again, the interpolating polynomial. And so after defining the basis vectors, like after defining the van der Waals matrix, we calculate here the interpolating polynomial by the summation of basis vectors, weighting them with the y value. That's all we have to do. And if I run this, I think I just plot, I've got a few things just to show you. We're going to plot the data points. I'm going to plot the interpolating polynomial, that's the y. And I'm going to also plot to see, so you see how it's constructed, the two basis vectors, what I called LB0, Lagrange basis subscript 0, Lagrange basis subscript 1. We'll plot both of those. And so here they are. In magenta, the two data points on the far left and right. In green, the interpolating polynomial, y, that we just constructed with the Lagrange basis vectors. Look, it's the same polynomial that we found with the linear algebra approach, because there is one unique polynomial of this order 1, that passes through the data points. We're just using two different approaches to find it. So we found the same polynomial. But this time we use these basis polynomials to construct it. And I plotted the two basis polynomials here. In red is the basis polynomial we call LB0, and blue is the basis polynomial we call LB1. Remember their features. So here I put it LB0, the first basis polynomial is 1 at the location of the first data point, and it's 0 at the location of the second data point. So it has that feature. The second basis polynomial is 0 at the first data point. It's 1 at the second data point. And so this green interpolating polynomial is just the sum of these two polynomials weighted by the y values at the two data points. So we weight the red line, the 0 basis Lagrangian basis function. We weight that by the y value 1.5. And the blue one, we weight by the y value of the second data point. We weight it by the 4. And the combination of those two produces the green curve with the interpolating polynomial. Okay, so that's the second method. I also wanted to show you in this cell, you won't be surprised here, that in the various packages in NumPy and SciPy, linear algebra packages, there's interpolating packages. So there's a package interpolate, and in there's a method of function Lagrange, and you can call that method, that function Lagrange. When you call it, you give it the arrays containing your data points. So you give it an array of the dependent variable and the independent variable. So the xi's and the yi's, those are the arguments. And then it returns the interpolating polynomial. So the return is from calling this Lagrange function with the independent variable array, the dependent variable array is the interpolating polynomial. It's the return. It returns the interpolating polynomial in a form that is a polynomial object. And I don't think we've met a polynomial object in Python before. We've met all sorts of objects, right? We've met integers, they're objects, complex numbers, objects, matrices, vectors, objects. There's a type called a polynomial object, and that's what's returned by this. That polynomial object allows you to calculate the value of the polynomial given at a certain value of x, the independent variable. It allows you to plot the polynomial as a function of that independent variable. It allows you to print out in text form what the polynomial is, and it allows you to inquire what the coefficients of the polynomial are. So the polynomial object comes with a number of methods that allow you to inspect, inquire, print the polynomial. So here I've got from this one function call, I've got the polynomial, but I'm just showing you some of the things that you can do with the polynomial. The polynomial object. So look, here I just print poly. I'm printing the polynomial object. What does it print? It prints this little guy here, 0.83x minus 0.17. It's the constant value. So this is the interpolating polynomial. So literally written it out. So the polynomial object, you can print it. I plotted, if I give an argument, a numerical argument here, it will calculate the value of that polynomial at the location of the argument. So I'm passing the x value of 2, the x value of 5. Those are the two data points. And it will return the values of the polynomial at those two locations. It's 1.5 and 4. And those were the dependent variable. Those were the values of yi at the xi's. So it is a polynomial that goes through the data. You can print out or construct a vector that contains an array that contains the coefficients of the polynomial. So I did that here. This picks out the coefficients. This constructs a vector that contains the coefficients. So when I print this quantity, it's just giving me this little vector here, two-element vector, two-element array that contains the two coefficients. Finally, down here, I call it, rather than with a single numerical value, I call it with an argument that's the array x, this proxy for my dependent variable. And so it's going to give me the curve, discrete curve, that is the polynomial. And so we can see that on the plot. And so here is the two data points again. This is the plot of polynomial, poly versus x. So that is that interpolating polynomial. So this is a Lagrange method again to solve this problem. But the function is using the function call is using the Lagrange method and just returning to us the interpolating polynomial. We're not actually computing Lagrange polynomials themselves. If I scroll back to this case of where I did calculate the interpolating polynomials, so that we could take a look at the individual interpolating polynomials. This was fine when I had two data points. And it's okay if you have three data points or four data points. Your expressions for the interpolating polynomials get a bit more complicated, but they're manageable. But obviously, if you had 100 data points, you don't want to be calculating your own Lagrange basis polynomials. So that's the reason that, after 2, 3, 4 data points, you'd be using the Lagrange function to find your interpolating polynomial. You could also be using your matrix algebra, but again, you'd have to construct the van der Waals matrix, and that gets laborious if you've got a lot of data points.
Yeah. How computationally intensive is this, like, compared to?
Yeah, so that's a very important question, actually. And it's the reason that one reason that you might prefer the Lagrange basis polynomials over the matrix algebra approach is if you have a very large number of data points. Then in the matrix approach, you are constructing a very large matrix, doing large matrix multiplication. Whereas with the Lagrange polynomial, you're not constructing that with matrix, constructing just a number of polynomials. So one's going to probably scale as n, the Lagrange method. One's going to scale as n squared, the matrix method. So I think that's a reason that if you were using this for a large number of data points, you would use the Lagrange method. It's also, if you use the matrix method, you have got to construct the van der Waals.
Yeah.
I just wanted to show you, so the homework for today's class is to use these two methods, but for four data points, rather than for the just 2 data points. So with 4 data points, you don't have the intuition about what the solution is for the best qubit that goes through 4 data points. But you'll see that with this, I did a similar problem, not with the same data points. Here are 4 data points. And so I define the 4 data points with a pair of vectors, a vector xi for the independent variable, yi for the dependent variable. And then I went ahead and found the interpolating polynomial through these 4 data points. So it's going to be we've got 4 data points. It's going to be the unique interpolating polynomial is a cubic polynomial. And whether we find that cubic polynomial and its coefficient with the matrix algebra method, or whether we find it with the Lagrange basis function method, we're going to be finding the same function. So you apply both methods, and you should find the same function. What you can't guess is, exactly what this polynomial looks like based on 4 data points. Here's the calculation I did. That's not good. I'm going to run the whole thing. I need the data for the matrix method. So we talked about this earlier on. You have to construct your van der Waals matrix, and now since the lowest order polynomial is cubic, I need a van der Waals matrix that runs from the 0th power up to the cube of the independent variable. So that's what I've constructed here. This is what I have to change. I didn't have to change the way I solve using matrix algebra functions. I solved for the coefficient of the interpolating polynomial. Just call it, again, with my 2 arguments, the van der Waals matrix containing the independent variable and the vector yi that contains the dependent variable. Once I get the coefficients, I can then construct the polynomial that passes through the data points. And here's that interpolating polynomial. Now it's the sum of these 4 terms, which are the 4 elements of the vector A. Here, just so you can see it, this is the van der Waals matrix in this case. It's now another 2 by 2 matrix, 4 by 4 matrix. The first column is just the ones of the van der Waals matrix. The second column is the data points, the independent variable data points. The third column is the square of them, and the 4th column is the cube of them. So, for example, we've got the second data point has xi is 2, square is 4, cube is 8. This is the vector A, or the array A, that's returned by that solve function that contains the coefficients of the interpolating polynomial. So here are the 4 coefficients, and it's using those 4 elements of that array that I constructed the interpolating function, and then I plotted somewhere. Where I plotted it. Big plot there. Where's the plot? Plotted here the interpolating polynomial. So this is the cubic function that we've arranged that goes exactly through each of the 4 data points. So then I did the same thing with the Lagrange basis approach. And this is where I started to learn that this is going to get really painful.
Yeah.
If you go to more data points, right? Because it was so easy to make a mistake on this arrangement. Yeah, there must be a better way of doing it.
You get in a rhythm.
Yeah, you get in a rhythm. I don't know if you come up with a better way of doing it, which I'm sure there is. But anyway, you have to, you see here, when you had two data points, that formula for the Lagrange basis function just has basically one term. And then when you've got three data points, you've got two terms multiplying each other. Now we've got three terms multiplying each other. Three terms in the numerator and three terms in the denominator. But these are functions that always ensure at the zero for the first or the second or the third data point, they're one at that data point and they're zeros at the other data point. So it's a very clever arrangement. Anyway, you construct these, and then once you've successfully built these, it's easy to construct the interpolating polynomial out of a weighted sum of those basis functions, which I did. And then you can plot all that. And on this plot, I drew both the basis functions and the resulting polynomial, the weighted sum of them. I wanted to draw the basis functions again to make this point. So the four basis functions are upstairs here. There's these four curves up here. The magenta one I can see from the plot is L0. I can see from the plot the magenta one is L0 because it's one at the location of the first data point. All the three others are zero there. The blue one must be L1. I can see that because the blue one is one at this second data point. All the other three are zero at that data point. And likewise, as we walk across, the red one must be the basis function for the third data point. It's the only one that's not zero there. And then the green one is the basis function for the last rightmost data point. It's the only one that's non-zero there. So on that plot, you clearly see this defining factor of the Lagrange basis functions, that they're always zero at the data points except their own data point, the one they own. Then you multiply them by the y values for those corresponding data points, and it just constructs this interpolating polynomial. And then finally here, of course, in practice, this is the way you would solve this problem. You call this one Lagrange function with the arguments of your independent variable and your dependent variable in these arrays, and it's going to return a polynomial object, which is that interpolating function. And yet again, it's the same interpolating function here again.